Hi. This work looks at optimizing resource-constrained applications that can trade output quality for the execution cost. For example, one of our benchmark application, Ferret, is an image query application that will iterate through a list of images in a folder and query a database to generate the top k similar images for each query image. The result is in the form of a ranked list per image. In an Approximate application, there will be one or more configurable components that can be tuned dynamically. We call them a knob. A combination of the knob setting is called a configuration. Application can choose to change the configuration by tuning one or more knobs during the execution. In our Ferret example, it has three variables that could have different values within a certain range. The vector of settings 8, 20, 25 forms up a configuration. Ferret can reconfigure at the end of each iteration, which is after processing every image. The result of tuning the knobs is that the application will now consume different amount of resource and generate different output quality. In the Ferret example, it will be finishing querying all images faster or slower and generate different top K results for each query image. To define such cost and quality, each of these applications come with a cost and quality metric. In this case, the execution time is the cost, and the quality is computed by this formula to compute the similarity between two ranked lists. One of the input will be the ranked list by running the application with the best configuration, and usually the most expensive one. And the other one is the list generated by running the current configuration. Here's a full example of the profile for Ferret, where each entry represents the cost and quality for a particular configuration. We can see that the more expensive configuration does not necessarily lead to a better quality, which makes the optimization problem non-trivial and interesting. A typical usage of such application is to tune the knob such that the application can finish within a limited resource. We call it a budget, which can be either execution time, energy, or power, with the goal of producing the highest possible overall quality. For example, collect as much data as possible for 5 hours from an underwater vehicle with the energy constraint of the capacity of the built-in battery. The problem also includes making decisions in advance to notify the user that the execution cannot be done within the budget. For example, refusing to start sailing so that we won't risk losing the vehicle. This type of applications exist in multiple areas. In this work, for illustration purpose, we only focus on the applications that use execution time as the cost. The problem to be solved is to find the optimal solution such that the overall cost of the execution is within the budget and produce the highest overall quality. The three key factors of the problem is to first, set up the trade-off space. Second, construct the cost and quality model. And lastly, perform runtime reconfiguration. There have been a lot of researches being performed on the single application scenario where theoretically the target application is the only consumer of the system resource. However, in multi-programming environments, the same problem have to be solved globally with all combinations of configurations in each application, which brings in new challenges to the problem. First of all, multiple applications will share and compete for the resource. Individual reconfigurations will potentially affect all others. In other words, a reconfiguration performed by application A may change the system environment and indirectly affect the decision of another application, application B. Such effect may trigger the reconfiguration from application B, and then the effect may come back to A. In some cases, such reconfiguration may trigger the failure of another application by violating the budget. This is similar to a situation where people share a boat. When a new passenger arrives, everyone in the boat tries to move to a position such that the boat does not capsize. However, such individual reactive decisions might not converge, with everyone moving back and forth and possibly ending up in the water in the worst case. There should be a plan that predicts in advance the best stable position for everyone on board in response to an additional passenger or when a passenger leaves. If for some reason some individuals need to move, there should be a predefined boundary so that the movement does not affect others. In multi-programming environments, the search space is exponential to the number of configurations per application, which is the second big challenge in this problem. The cost and quality profile for a single application may no longer be valid anymore, since such profile is usually trained when the target application is the only one running on the system. One naive approach towards the problem is, how about we train all combination of configurations and set up the profile? However, it is time-consuming and often infeasible because we do not know the real execution pattern. For example, what applications will be running against our application and how many of those will be running together. We cannot possibly train all the possibilities. Another approach is to let each application manage themselves individually, but again, it cannot handle the interference as mentioned previously. Or we could assume that the system will split the resource equally among the applications, but that's usually not the case, and according to our experiment, it underutilizes the resource a lot, meaning some applications will be assumed to be failing, but actually the system can just fit them fine. The rest of the presentation will be as followed. I'll first describe some terms I'll be using, and then the key observation that motivated our work. And then I'll introduce our prototype system RAPID-M along with its evaluation. Finally, the summary. Besides the knob and configuration I've described previously, here are some key terms I'll be using during the rest of the presentation. We use a vector of system metrics to represent the footprint of a configuration. The vector can be used to indicate how much workload does an application introduce to the system, or what is the overall status of the current system. The values for these metrics can be acquired through performance counters. In our case, we use the Intel PCM tool. Slowdown is the performance degradation of an application encounter when running under the system with a given footprint, or workload. A bucket is a group of configurations that generate similar footprints and have similar slowdown behavior. Lastly, we'll introduce two models for different purposes, a P model to map a footprint to slowdown, and a M model to aggregate two footprints to one. I will describe them in detail in the following slides. As mentioned before, the interference and the search space explosion makes the optimization problem much more complicated and hard to be solved. However, we found out that configurations in an application can be clustered into a few groups where all configurations within a group share a similar runtime behavior. Such runtime behavior is defined by how much workload does an application introduce to the system and what is the slowdown does the application encounter when running with this configuration when given a certain system environment. As an example, this slide shows the dendrogram from running the hierarchical clustering on the 700 configurations in FSE. The x-axis shows the ID of all 700 configurations. For simplicity, we truncate the graph by grouping a set of configurations and represent the set by a number within the parenthesis where the number is the size of the set. Subtrees in the graph show the result of clustering. The y-axis shows the average Euclidean distance within a cluster. In this example, all 700 configurations are clustered together at the root of the tree, the black dot. When moving downwards the tree, two buckets shown as the root of the two subtrees are formed with size 250 and 450, the two yellow dots. The height of each subtree reveals the closeness of all configurations in the bucket. Configurations within each bucket will have higher similarity in terms of system footprints when moving downwards the dendrogram. So, to ensure the similarity of configurations, we first let configurations in a bucket close enough to each other by setting a maximum distance threshold. For example, the dashed line on the graph, if we cut a tree with a line on y equals to 4, then all configurations can be clustered into 5 buckets. Then, for similar slowdown behavior, we try to construct a performance model to capture the relationship between slowdown and the execution environment for all configurations in a bucket. If we can construct such model, then it shows that these configurations will have similar slowdown behavior. As shown in the graph, 700 ferret configurations are clustered into 5 buckets, with a slowdown model being constructed with a mean relative error of 1.6%. Having such observation, we invented this local mechanism to reduce the problem complexity and minimize their interference. In the first step, we clustered the configurations based on their footprints and slowdown, and then during runtime, rather than searching from a combination of configurations, we'll search from a combination of buckets. In this step, the problem complexity is greatly reduced. Then, finally, application can readapt themselves within the assigned bucket. Given that all configurations in the bucket has similar behavior, reconfiguring within the bucket will not introduce great impacts to others. Therefore, the interference is minimized. In this solution, there are 2 key questions to be answered. First, how to determine the right number of buckets. Second, when iterating the bucket combinations, how to determine the optimality. To answer these questions, we'll introduce 2 key models in RAPID-M. The first model is the P model, P as in performance. It is used to predict the slowdown for an application when running under a configuration given the system footprint. When training the application, we collect the data by introducing artificial workloads to the system and record the system footprint when running the application alone, and then the system footprint of the overall system when the application is running with the artificial workload, and also its slowdown. By having this data, this model can be constructed. This model is application-specific and machine-specific, meaning the model keeps unchanged regardless of how many applications are running together, unless it's moved to a new machine. The second model is the M model, M as a machine. It is used to predict the overall system footprint when running 2 applications or more applications together. The input of the model is 2 footprint vectors, and then the output is another. When more than 2 applications are running, we'll recursively apply M model on pairs of footprints and have the final output. The model is machine-specific. When determining buckets, we first run a hierarchical clustering on all configurations based on their footprints, and then try to construct the P model per bucket. If we fail to construct a P model with a specific error threshold, we'll continue partitioning the bucket with the worst prediction accuracy until the threshold is satisfied. During the runtime, each bucket is represented by a footprint vector along with a P model. The machine is associated with a trained M model. During the reconfiguration, we will enumerate all combinations of buckets. Then for each combination, we recursively apply M model on a pair of bucket footprints and generate the final overall footprint. Then, we apply the P model given the predicted footprint to compute the slowdown for each application per bucket combination, and select the combination who satisfy the constraint that the slowdown for each application can still honor the budget. Meanwhile, the application overall output is maximized. Here we use the sum of application quality to represent the overall quality. Finally, when each application got the bucket assignment, it can reconfigure within the configurations in the bucket if needed. This is an overview of the implementation of RAPID-M. We provide a development framework built in Python so that developers can train the application and construct the P and M model along with the bucket. Besides, we also provide a server that keeps track of the trained models for all applications and do the runtime bucket selection. Finally, we also provide a C++ library for developers to engage RAPID-M's runtime control. For example, acquiring the latest bucket selection or triggering a local reconfiguration. Now that I've described how RapidM works and being implemented, we evaluate RapidM from different perspectives. First, the P model. We evaluate the model on 6 benchmark applications when constructing the P model. We pick the first best fit candidate from a pool of models. Also, we determine whether to use polynomial features for each model and decide based on the accuracy. This chart shows the model selection for each application with a prediction error below 2%. We then evaluate the M model for different system metrics using the same pool of models. To eliminate the noise, RapidM also performs a feature filtering process when constructing the model by eliminating irrelevant features. We compare the training time for different models, and we found out that the most time-consuming or complicated model might not be the best fit for a particular feature. For example, the most complicated model cost around 6 minutes to be constructed for L3 hit, but the model providing the best accuracy only used 40 seconds. For RapidM, it picks the best model by first selecting the best model when using all features, and then iteratively reduce the number of features used as input. It shows that RapidM reduced the M model training time to less than 5% for most features. For some features, for example L3-Mis, the select model can take longer to converge when only using selected feature. Both the evaluation on both P model and M model justifies our approach, where we have to explore more models than have a unified model for different features or different applications. After the construction of the models, we now evaluate how well RapidM works to make configuration decisions. To do that, we compared our approach with multiple heuristics of slowdown prediction. This slide shows an example execution trace where up to 4 applications can run together. The x-axis shows the timestamp. Lines with different colors represent the execution period of different applications. Dashed line followed by a cross represent failed execution due to running out of budget. Crosses without lines represent executions that got rejected to start at the beginning due to the strategy indicate the execution will fail. The trace on the top left corner shows the trace generated by running applications in random orders with unlimited budget so that they can all complete. Then we record the start time of each execution. We repeat the execution by running the application each with a budget that's just enough for the application to compete when it's running alone, so that when running this application with other applications, it would force them to go for a lower setting to adapt to the interference. We compare RapidM among 4 other heuristics, and we found out for applications that underestimated slowdown, applications may potentially use a higher setting at the beginning and eventually leads to failure of completion. On the other hand, approaches that overestimate the slowdown may make the application think that he can never survive, so more executions are rejected to be executed when it could. We summarize RapidM's benefits relative to other strategies on 45 traces, each with 10-minute length, using different budget settings. This figure shows the average results of the trace where up to 2, 3, or 6 applications running together. We run the experiment on a 4-core machine, and overall, by using RapidM, more applications are able to be completed and achieve the higher overall quality with less reconfiguration during the execution, especially when the system is busy. To summarize, we use the footprint vector as an abstraction for configurations and enable the configurations to be bucketized based on runtime behavior. When determining the global optimal solution, we partition the problem into 2 smaller sub-problems. First, to predict the overall environment by M model, and then predict the slowdown by P model on the bucket level. Then we introduced the local-global-local approach that enabled more successful runs and achieved a higher quality for the 6 applications, especially when the system is busy. Thank you.